second
Mathematics
seminars. Michelle Hayek as a speaker. She's a doctoral candidate in industrial engineering at University of under practicum. Her research focuses on the health mathematics and the health and at home self monitoring. Michelle has a robust background in analyzing healthcare data sets and so topic today is logic and implement.
Hello, everyone, and thank you for the introduction, Sayun. So today's topic is logistic regressions in R. I'm gonna talk about a brief introduction of what a logistic regression is, the assumptions that it takes, and how to implement it using R. So what is a logistic regression? A logistic regression is a statistical model that is used for analyzing data sets where there's one or more independent variables that determine a certain outcome. Now, the outcome is measured with a dichotomous variable, so a binary variable where there's only two possible outcomes. The purpose is to predict the probability of a binary outcome based on these one or more predictors. So this is a good representation of how it works. We can see the probabilities. They're bounded between 0 and 1, and we can see the outcome variable that is either 1 or 0. And usually the threshold that is used in this case is any probability below 0.5 would be considered a 0 for the y outcome, and anything above would be considered a 1. So we're going to talk about an overview of how we go from probability to odds and then to log odds, which is the equation that we use. So first of all, a probability ranges from 0 to 1, and it's the likelihood of success of an event, which is represented by P. And it's the probability it represents the chance of an event occurring. The odds ranges from 0 to infinity, and it's the ratio of the probability of success to the probability of failure. So it's basically P over 1 minus P, so success over failure. It means the odds provides a measure of how likely an event is to occur. The log odds ranges from minus infinity to plus infinity, and it's basically the log of the odds. And it transformed the odds onto a linear scale for easier interpretation and analysis. Now, how do we do that? The probability equation is 1 over 1 plus e to the minus beta 0 plus beta 1 x1 until beta n xn, where the probability is the probability that the dependent variable y is equal to 1, so success. The x variables are the predictor or the independent variables, and beta 1, beta 2 are the coefficients of the predictor variables. Now, when we want to convert the probability to odds, we basically do the probability over 1 minus the probability of success. And then when we want to do the log odds of that, then we can see that we end up with a linear relationship. Now, why do we do all of this? Why do we go from probability to odds to log odds? The first reason is, like I said, it provides a linear scale that allows for easier interpretation across different probability levels, like we saw from this equation. There's symmetry. So probabilities, they range from 0 to 1, with 0.5 representing equal chance of success and failure. Odds range from 0 to positive infinity, with 1 representing equal odds. And log odds center around 0, making it easier to interpret positive and negative values. So if we see an example here, we can see how the log odds has this sort of symmetry showing the negative and positive values. The third reason is the logarithmic scale. So logarithms compress large or small numbers and make it easier to work and interpret. And it's robust, so it's less sensitive to extreme values and outliers compared to probabilities, which make them more robust for the analysis. Now, the assumptions that the logistic regression takes. The first one is that the outcome is a binary or dichotomous variable, so 0 or 1. The second thing is that there's a linear relationship between the logit of the outcome and each predictor variable. There's no influential values, extreme values, or outliers in the continuous predictors. And four, there is no high correlations or multicollinearity among the predictors. And to improve the accuracy of a model, you should make sure that these assumptions hold true for your data. So now that we talked about a brief definition, I'm going to show you an example in R. Okay. So first, I'm going to load the libraries. And the data that we're going to use is called Pima Indians Diabetes 2. And it's a built-in data set within R. So the first step here is we're omitting any NA values from the data set. We have 392 rows and 9 columns within this data set. And we can see a brief description of what it represents. So the pregnant variable represents the number of times the female was pregnant. Glucose is the plasma glucose concentration. Pressure is the diastolic blood pressure. Triceps is the skin fold thickness. Insulin is the 2-hour serum insulin. Mass is the body mass index. Then we have the diabetes pedigree function, the age in years, and the class variable for diabetes, negative or positive. So the main outcome in this example is to determine whether a patient has diabetes, yes or no. So the goal is to predict the probability of diabetes test positive based on the clinical variables. So in R, this is how you do a linear regression, a logistic regression model. So use the GLM function with the family being binomial. Diabetes is the Y outcome. And then this basically represents that you want the X variables to be everything other than diabetes in the data set. And the data that we use is Pima enzymes. So after we run the model, we can look at the summary outputs. So a brief explanation of what this output is. First of all, we can see from here which variables are the most significant ones. So we can see that glucose, mass, and pedigree are good predictors of whether a person has diabetes, positive or negative. If we want to interpret these values, this basically means this is the coefficient. So that would be beta 1 glucose. So this basically says for every 1 unit increase in glucose, the logit of the outcome variable increases by 0.038. And for better interpretation of these results, we can convert the coefficients into odds ratios. So we're basically going back and presenting them in odds ratios. So this is probably better to see. So for every 1 unit increase of glucose, the odds of having diabetes positive instead of negative increases by 0.04. We can also print the confidence intervals for each of these coefficients. So we can see the range. So glucose ranges from 1.03 to 1.05, and it's significant. We had mass was also significant, and we can see the ranges. So this is a general description of how the logistic model works and how we implement it and determine the results. Now for the diagnostics. So the first thing that we talked about is that the outcome should be a binary or dichotomous variable, so 0 or 1. And by using summary of the data set, we can basically look at a small summary of each variable inside of the data set. We can see the min, the max, the mean, and so on. So we can look here and see diabetes has only negative or positive. So the first assumption is satisfied. The second thing is that there's a linear relationship between the logit of the outcome and each predictor variable. Now, in order to do that, we have to have the prediction, the probabilities of each variable inside of the model. And so, like we said from the graph, everything above 0.5 would be considered as diabetes positive, everything below would be negative. Now, we only select the numeric predictors in our data set because this is what we want to see, the linear relationship. And then after we add this to the main data set and convert it to a logit and do the log of the probabilities, we can basically see the relationship across each variable. So we can see here that age, it sort of has a linear relationship, but it might need some transformations in order to be more linear. And by transformations, I mean we can do add the power 2 of the age or log of the age to make it more linear. Glucose seems to be sort of linear. Insulin, mass 2. Pedigree looks to be a little bit not linear, so this might need some transformations too. And the rest, they sort of look linear.
Wait, Michelle, what is pedigree?
The pedigree is the diabetes pedigree function.
Like what?
Pedigree function. This is how they defined it in the data. Yeah. So this is the range of the variables. Now, the third step is we want to check for any influential points. Now, before I go into this, does anyone know the difference between an outlier and an influential point? I can give an example. If you look at mass, let me make this larger.
Age, you can see the top point. So that's an outlier.
Okay.
That would be an outlier. And things like influential points will probably be the ones that are not as close to the trend, but are in between, kind of. If that makes
So if I gave you mass and pedigree, and I'm looking at this point versus this point, which one would be an outlier? Which one would be an influence?
sense. The pointing on
This one versus this one.
the one on the pedigree would be a outlier
Why?
because it's so far from everything.
Okay. And this would be an influence?
I would say so.
Why?
Because it's still within the trend, but it's not inside the trend. Does that make sense?
It's the opposite.
Yeah.
So it's actually the outlier is the number that is far away from the mean, but it doesn't really affect the model that much. The influential variable is what is actually causing the model to twist to an angle to reach that point. Does that make sense? So what we want in the data is we want to make sure that we don't have any influential data points that might cause some changes in the coefficients for the model. So that's where we go into step 3. Now, this is the code to basically look at whether we have any influential points. And this is a graph showing the standard residuals. So this is basically showing how far is the predicted outcome from the actual value. So the predicted y versus the actual y. And any value above a standard residual of 3 would be considered an outlier. So if we do this in our data set, it turns out we don't have any outliers or, sorry, any influential points. But if you have any influential points in your data set, then you would want to remove it or see what you can do with it so that you get a good outcome. And finally, we want to check for multicollinearity. So this is a function within R. And as a rule of thumb, a VIF value that exceeds 5 or 10 would indicate that there's a problematic account for multicollinearity. In that case, we don't have any variables that have multicollinearity. But again, if you do, you would want to consider maybe removing one of these variables or being careful for all these things. Yeah, and this is everything. Thank you for being a part of this and listening to me.
Before you take off the recording, as we're still on.
Yeah.
Going back to the influential point and outliers, I think I'm gonna summarize what I heard. Outliers are okay in the data, you leave it alone. Influential points, if you detect them, you should consider taking them out, although that it is not a given that you can take them out.
That's true. So sometimes when you're dealing with some of the data, you might not be able to remove an influential point from the data set. So what you can do in this case is keep the patient there or the data point and then see how much it affects the model. If it really changes the coefficients of the models, then you might want to consider removing it from the data set. If it doesn't, then you can keep it.
Right, because I think what I heard from you in terms of the definition of an influential point is in my way of speak, it's a leave one out analysis. You
Yeah.
take a point out, you run the analysis, you see how much it's changing when that point is in or out. And
Yes.
if you have the model shift quite a bit with one point, you wonder whether that point should be included when you're taking the average. Is the point of this.
Yeah.
Okay. Thank you.
Yeah.